Okay, we're going to continue on here, chapter 15. And we've been talking about KSP, which again, as we've been talking about, is really the solubility product equilibrium. And it is an equilibrium constant like any other, but it is really more specifically for things that are insoluble. And because of that, typically the way the reactions and equations are written is, as we talked about, pretty much always solid there on the left-hand side or reactant side. And again, our aqueous sort of ions on our product side. So when we do our KSP expression, again, just the products, as the reactants are usually a solid and not included. So remember that if you have just a KSP value, you do need to do an ice table. We do that ice table with S typically, which is the molar solubility. And that is basically the molarity of everybody. And we can also, if we know the solubility of a compound, either in any units really, grams per liter, moles per liter, any type of unit, we can actually use that and sort of figure out the KSP value for it. They are typically very small values for KSP, and that's again because they are for things that are typically insoluble. And because they're typically insoluble, that means most of the time they're hanging out over here on the reactant side, which means, again, if we just think about our products over reactants, we mainly have a lot more reactants, which means K is going to be a relatively small value. And that's typically what we see with KSPs. Some of them are really incredibly small, like to the minus 56, minus 30 something. So really, really small sort of values. All right. We also talked about, I think, last time as well, that there is only really one situation where you could use the KSP values to compare solubilities between different compounds. And that would be a case when they break apart into the same number of ions. So if they do break apart into the same number of ions, like they both produce two ions, then you can actually use KSP values to make a prediction as to which one would be more soluble, which one would be less soluble. And again, the larger KSP value would mean that that guy would be more soluble than the guy with the smaller one. Again, because of a larger KSP value, you would have mainly products at equilibrium, and that's aqueous, which means it should be more soluble than somebody with a smaller KSP value. We also saw in that table on the very last slide, I think, was if you are comparing things that actually do break apart into different numbers of ions, you do actually have to go through the calculation and calculate the actual solubility of everybody, and then compare them. The KSP value will not basically do you any good. Any question on that stuff there from last time? All right. Then we're going to talk about some things that do affect the solubility of a compound. And as we talked about, I think at the very beginning, sometimes we think about solubility rules as always being the case. So if the solubility rules say that it should be insoluble and you should get a solid, you always think no matter what the situation is, you will get that solid. But there's actually a lot of things that can affect whether or not, for example, you will actually see the solid form. One of the things that can have an effect on solubility is the common ion effect. And this is sort of the same effect we saw with buffers. The presence of a common ion, right, will basically push the equilibrium back the other way. And since this is a KSP equilibrium, as I just mentioned, we have solid on the left, we have aqueous ions on the right, which means if we have a common ion, it will always be on the right-hand side here. It will always be on the product side. And Le Chatelier's principle is going to tell us that that should cause the equilibrium to shift away from it. And what that's going to do is cause basically that compound to stay together more than it normally would. And the solubility will start to decrease because of that common ion effect that will occur. So, for example, if we look at the solubility here of, say, silver bromide in water, the KSP for silver bromide there is 7.7 times 10 to the minus 13. If we go through it here and do our sort of ice table here to figure out the solubility, we got a silver and we got a bromide, basically. Initially, we have 0 and 0, change plus S at equilibrium, S and S. This would go into our KSP expression of the silver ion. times the bromide ion, and that would equal 7.7 times 10 to the minus 13. And that would get us basically S squared equals 7.7 times 10 to the minus 13. Obviously, square rooting both sides there will get us really a molar solubility here of silver bromide in water of approximately, we'll call it 8.8 times 10 to the minus 7 molar. That is a relatively small amount there in terms of solubility. Roughly, just do a quick calculation, times that by like 187.8, which is the molar mass. You're looking at roughly 0.000, roughly 0.000165 grams per liter. So again, you're not getting a lot of it to dissolve in basically a liter of solution. Now, if we look at this same sort of situation, but instead of just trying to dissolve this in water, we also have in that sort of water some sodium bromide. And the sodium bromide here is going to be our common ion. Let's use up here to do it. So what's going to happen in this case when we put it in the sodium bromide, because that is a salt, it will break apart. And obviously here we'll get some sodium ions that's going to float around and some bromide ions. And it is that bromide ion that is our common ion. So if we did our ice table again in this situation, initially we would have zero this, but we would have some bromide as contributed by the initial concentration of our sodium bromide, and it would be the same, 0.001. The change here would be plus S and plus S. That means at equilibrium, we have S and 0.001 plus S. This again would go into our KSP expression in this case, and we would get S times 0.001 plus S equals our 7.7 times 10 to the minus 13. This is definitely a small value of K, which means in this case, you could also still do your assumption, and you could assume in this case that S is going to equal to 0. And this again is going to be only the S that we're going to be adding in this case to something. So that's the only one that we're going to get rid of. This will give us basically S times 0.001 equals 7.7 times 10 to the minus 13. Obviously, we're going to divide that to the other side. And we're going to end up with, in this case, something like 7.7 times 10 to the minus 10 molar as the molar solubility here of silver bromide when sodium bromide is together. And again, just a comparison, it's roughly, I think, something like 0.12345614446 grams per liter. So you can see the solubility here in the common ion is much less than the solubility there in water. And again, it's because of the presence of this common ion to start with, going to cause the availability of our products to be more than our reactants and going to force the equilibrium back in this direction and going to basically keep the thing together. So one thing that could affect the solubility here in a way that actually will not allow it to actually be more soluble, actually will cause it to be less soluble, is the presence of some type of common ion, as it will basically keep that guy or force that guy to stay together. Any questions on that there? All right, so why don't you maybe try one, I think. There we go. Silver chromate it has a KSP of 9 times 10 to minus 12. What would be the solubility of this compound in 0.1 molar potassium chromate? We'll do both. Why don't we do molar solubility, and let's do actually grams per liter as well. So silver Again, 107.9. Chromium 52. And oxygen. All right, so let's take a look. So once again here, we have some silver chromate, and that definitely is going to be insoluble. And again, we know that because it has a KSP value. So we can set up that sort of equilibrium here where this guy is just going to break apart into its ions. And in this case, we will get a couple of silver ions in this case and a little chromate action happening there, maybe. This will give us a, KSP that is basically the silver. It does need to be squared because it's coefficient there times the chromate. And that would equal basically our 9 times 10 to the minus 12. We also, though, have it in this solution some potassium chromate, which is K2CrO4. That is a salt, which means it is not going to set up an equilibrium, but will just break apart into ions. And in this particular case, as you might imagine, it is the chromate here that's going to be our common ion between those two. The potassium chromate has a molarity of 0.1 molar. It is a 1-to-1 relationship between that and the chromate, which means the concentration of the chromate is also going to be 0.1 molar. That's important here because this will be 0, and we will need, again, a starting concentration there for the chromate. If we do not use the starting concentration for the chromate, we're basically doing the calculation of silver chromate and water basically dissolving. So if you don't put that in there, you're basically not doing the common ion part of the problem. Change here is going to be plus. Remember, we still need to take the coefficient there, so that's going to be a 2s. That's also going to be an s, and that means here at equilibrium, we got a 2s and a 0.1 plus s. Any questions on the ice table there? All right, like normal, we're gonna slap that thing right into our KSP expression here, and that's gonna give us 2s squared times 0.1 plus s equals our 9 times 10 to the minus 12. Once again, here you can make an assumption here that s is equal to 0. In most cases, you should still really check it. I may have skipped checking it last time, but you really should check it. But I would say probably in most cases you're going to be okay because these KSP values are really small. So usually you're in good shape. We are going to get rid of this one here, and that's going to give us basically 4s squared times 0.1 is equal to 9 times 10 to the minus 12. Obviously here we could take 4 times 0.1, going to give us 0.4 s squared equals 9 times 10 to the minus 12. We're going to divide, and then we're going to square root it. Yeah, so we'll take 9 to the minus 12 divided by 0.4, a little square rootage. There it is. And we're going to get like, a super small number. I don't want to write to zeros, so let me try that again here. Let's do that. There you go. We're going to get an S of about 4.7 times 10 to the minus 6. Again, we should check it. So if you took that divided by 0.1 and times it by 100, you're like at 0.004%. So the estimate there, our assumption is good. Check is good. So that is the molar solubility. So remember, when you do solve for S, that basically is the molar solubility. So the molar solubility here would be 4.7 times 10 to the 6 molar. And again, it works out because essentially if you put the S into here and you times it by 2, but then you go from this guy back to that guy, you're going to divide by 2, and it'll basically come back to S. So it's all basically going to be the same here. That is to go from molar solubility, which is basically moles per liter, to grams per liter. We do need the molar mass to do that. So that's going to be 2 times 107.9 for our silvers, plus a 52 for our chromium, and 4 times 16 there. So the molar mass of this guy is looking like about 331.8 grams per mole from the periodic table. We'll use that as a conversion factor, 331.8 grams per mole. Moles will cancel. That will turn us into grams per liter in terms of our solubility. 4.7 to the minus 6. And that's going to give us a whopping 0.00156 grams per liter. Is that a lot of solubility? That is a very little amount of solubility. Basically, you take 0.002 grams and dissolve it in 1,000 milliliters of water, basically, right? So that's basically nothing, basically, in this case, yeah. Any questions on that calculation there? Okay, so this is one really sort of major effect that you could have on solubility is the presence of those common ions. And much like what we saw with weak acids and weak bases, it basically will keep the compound together. Now, another sort of factor that can affect solubility is actually pH. And the presence of common ion, as we just saw, will decrease the solubility. Now, if you have an insoluble base, it typically will be more soluble or will dissolve in acidic solutions. Or if you have an insoluble acid, it typically will be more soluble or will become soluble if you put it in a basic solution. So, for example, if we look at this sort of KSP here of magnesium hydroxide, it has a KSP value of 1.2 times 10 to the minus 11. So if we ran through our normal sort of ice table here to figure out some solubility of everybody, we would have 0, 0, plus S plus 2S in this case. And at equilibrium here, we would have S and 2S. The KSP here would be the magnesium times the hydroxide, and we do need to square it. So if we put our numbers in there, we would have 1.2 times 10 to the minus 11 would equal S times 2S squared. So if we do all that good stuff, remember you also need to square the 2, which is oftentimes forgotten by people. So that's going to give us like a 4S cubed, I believe. And we're going to then divide this to the other side and also take the square root afterwards. So we're going to divide and then square root it. So if we do that there, 1.2 to the minus 11 divided by 4, and then not square root, but take the cube root of it there. So we're going to take the cube root, which again on your calculator, you could either caret it, and take 1 divided by 3, which will give you the cube root. Or if you have that button that will do it for you, you could actually use the button that's on your calculator. Usually on your calculator, you have like a button. Sometimes it looks like that. You could use it as well. Regardless, whichever way you want to do it, caret 1 divided by 3, however you want to do it. You will end up with 0.000144 molar. That is what our S is equal to. In this case, though, if we're looking at pH, in this particular case, it is actually the hydroxide that's kind of important here. And if we want the concentration of hydroxide, it actually equals 2 times S. So if we take 2 times our S value here, we will end up with 0.000288845. That will allow us to calculate the POH minus the log of what we just got there. That's going to get us a POH of about 3.54. And finally, I'll come up here. The pH would equal 14 minus 3.54. Roughly a 10.46 pH. First off, any question on that? I think we saw a little bit earlier as well in another example. Here we could actually figure out what the pH of this solution should be. So this solution here in water should have basically a pH of about 10.46. It is a base. It's an insoluble base. And that's sort of the baseline pH of it. Any questions on that? So what would happen, for example, if I took the pH, if I dropped the pH or took the pH to less than 10.46? So if I decide I wanted to actually drop the pH lower than that 10.46, usually the way that you can lower a pH is you add acid or base. You add acid, right? So if we add some acid to this, we're essentially going to be adding like H plus, right? When we add some acid. Now, when I add acid to this equilibrium, the H plus most likely will react with what thing? Since obviously H plus is not in equilibrium, but H plus will most likely react with hydroxide, right? Because H plus will react with the hydroxide that's there. And when you have H plus and hydroxide, you make water, yeah. And essentially what that's doing when it reacts with the hydroxide is you're going to make water. It is essentially doing what to the hydroxide concentration? Is going to be essentially removing the hydroxide concentration. And based on Le Chatelier's principle, that should cause the equilibrium to shift towards the hydroxide, right? Or towards the product side. And when it causes that shift to the product side, that means we're actually going to have more aqueous ions than solid, and that will actually increase the solubility of it, right? We'll get more of it to actually start to dissolve in this case. So more will dissolve because the equilibrium is shifting to the right, causing more of that solid basically to break down to make more products in that case. Question. Do I need to get it to go all the way to an acidic pH to see that happen? The answer is no. You just got to drop it less than 10.46. If you actually drop it to something like a pH of like 9, you'll get a significant amount of it to actually start to dissolve because the baseline pH of where it's starting is 10.46. So as long as you drop it below that 10.46, even though you may still be in a basic pH, that's still going to cause the same effect to occur because you're still adding that H plus. It's still going to react with the hydroxide and it's still going to cause water and make the equilibrium pull to the right. So sometimes people think you got to get all the way down to an acidic pH. You don't. If you do, you get almost all of it probably, or a good amount of it probably to pretty much dissolve. But you actually just need to drop it below that baseline of 10.46. So that is why that 10.46 is an important number to know because that's sort of your baseline of going up or down in pH and causing that sort of effect to occur. Any questions on that? Now, let's just say the opposite. I decide that I want to actually take the pH above 10.46. And if I'm going to take the pH above 10.46, that means I need to raise the pH, which means most likely in this case, I'm going to add a base. And that means I'm going to really add hydroxide. So when we get to this part of the situation here, and we actually are going to bring the pH up, what we're actually doing is affecting hydroxide in this case as well, but it's going to be the opposite effect here because we are adding more of this. We're actually increasing the amount of hydroxide that's going to be in that equilibrium. So the hydroxide will go up in this case. And when the hydroxide concentration goes up, that again, based on Le Chatelier's principle, should cause the equilibrium in this case to shift away from it, which will shift it to the reactant side. And on the reactant side, that is where we see more solid. So what would happen in this case is if you added some sodium hydroxide to this and brought the pH above 10.46, you would actually cause it to start to precipitate out more because it's going to shift the equilibrium to the solid. Those ions, a little bit amount of ions that are floating around will then start coming together and actually making more solid. Any questions on that there? So pH plays a really big factor in, again, whether or not you will see something precipitate out or not precipitate out. We don't do these type of experiments anymore, which are known as qualitative analysis experiments. And it's really all about this type of thing. And there's a lot of weird steps that sometimes when students do it, they don't understand like why they're doing that. And there's steps like, make it acidic and then make it basic and then make it acidic again in the same sentence, basically. And the idea of doing a lot of that is to get it into the right pH so you can see something precipitate out when you want it to precipitate out, keep other things in solution where you don't want them to precipitate out. Any questions on pH and solubility? All right. Now, we could also look at, as we talked about at the very beginning, whether or not we would predict a precipitate to form, and that we can use Q versus the KSP value. And again, if Q is greater than the KSP value, we'll get a solid that forms. And if Q is less than the KSP value, we will not get a precipitate to form. A reminder again, KSP and Q are calculated the same. It is just basically our products over our reactants. And again, in this situation, much like we've been seeing, you pretty much will not have any reactants. So it's basically just the products. Again, you calculate Q the exact same way as you calculate the KSP. So let's take a look at this here and try to decide whether or not a precipitate will form. So if we took 2 milliliters of sodium hydroxide and we added it to 1 liter of calcium chloride, will a precipitate form? So the first thing we want to think about is what is our possible options for a precipitate to form? And since sodium is basically a source of sodium ions and hydroxide ions, and calcium chloride is basically a source of calcium ions and chloride ions, we have to think about solubility rules and really switching our partners here and seeing if anyone would perhaps make a solid. And in this case, when we do that, we will see that calcium hydroxide um, is a possible solid that can form. By the way, you could also look at the KSP table if you don't know your solubility rules. And if you see calcium hydroxide on there, you know that's a possible guy that's going to make a solid in that case. Now, the KSP for calcium hydroxide is 8.0 times 10 to the minus 6. So here, if we want to know whether or not it is going to precipitate or not, we do have to figure out Q and compare it to it. So why don't you take a few moments there and calculate Q in this situation and compare it to the KSP and see if we basically want to calculate Q, and Q is calculated the exact same way as we would our KSP. Here we are dealing with calcium hydroxide. So when that breaks apart, we would get a calcium ion and 2 hydroxide ions here. And again, that would mean that our Q would be basically the calcium concentration times the hydroxide concentration squared. We do want the correct concentrations of everybody. And what I mean by that is when we take our sodium hydroxide and dump it in here, along with our calcium chloride, and it goes for a swim, we need to actually get our molarity of everybody in the mixed solution. So a little M1V1 equals M2V2, as the molarities will change since the volume is changing right when they all get mixed together. So really the concentration of hydroxide, which comes from basically the sodium hydroxide, would be in this case 2 milliliters times the molarity. And in this case, I'm going to divide by the total volume here. And since they are in different units, I'm going to convert everybody to milliliters. So I basically have 2 milliliters of my sodium hydroxide, and 1 liter is 1,000 milliliters of my other guy. So basically 1,002 milliliters. So we'll go 1,002 milliliters. Milliliters will cancel, going to leave us molarity here. Again, since we're using dilution equation, we don't really have to convert it to liters, but you could if you wanted to. Divided by 1,002. That's going to give us a hydroxide concentration like 3.99 times 10 to the minus 4 molar. We need to do the same thing here for our calcium ions, which obviously are going to come from our calcium chloride is going to be our source of that. And for the calcium, we are using basically 1,000 milliliters or 1 liter. And the molarity is 0.1 molar. And that's going to be divided by our total volume as well. So our milliliters will cancel. And we will get 1,000 times 0.1 divided by 1,002. And go 9.98 times 10 to the minus 2 molar. Good questions on that there. These are really the concentrations of these guys that we do want to, again, put into here. So our Q will equal our calcium 9.98 times 10 to the minus 2 times our hydroxide. Again, don't forget you do need to still square it. So we'll go 3.99 to the minus 4, a little squaredness there, times 9.98 to the minus 2. Gets us like a 1.6 times 10 to the minus 8. At this point, we want to compare Q to the KSP value. And in this particular case, Q is actually less than the KSP value. Yeah. That means, would I expect to precipitate in this case? We would actually get no precipitate in this case. Again, it would point opposite of where that's pointing. It would send it to the product side. And again, on the product side, we would have aqueous ions. So this is another really important sort of example of what affects solubility. Even though solubility rules tell you if you put these two ions together, you should get a solid, a factor like, do you have the right concentration of those guys is really important. And if you don't have the right concentration, you will not see that solid form. So those are three things that could really affect the solubility of something, whether or not you will see or not see the solid form. Things like presence of common ion, proper concentrations of the ions that are floating around, and pH are all three factors that have a really big effect on solubility. And again, sometimes we think about the solubility rules that maybe they beat into your head that, they always happen no matter what the situation is, but there's a lot of factors could definitely affect the solubility situation. Any questions on that there? Okay. All right, the next thing we're going to actually talk about is a really practical sort of aspect of KSP and basically using KSP to help us do what is sometimes referred to as selective precipitation. And what that essentially means is, for example, in this particular here, we want to know what concentration of silver would be needed to precipitate out only silver bromide in a solution that contains both bromide ions and chloride ions. So essentially what we have here is a solution, and we have bromide guys floating around and we have chloride floating around. And essentially what we want to figure out is if I add some silver to it, we definitely will get two solids that could form. We will get silver bromide and silver chloride based on solubility rules, right? Chlorides are soluble in everything except for lead 2, mercury 1, and silver is an example here. Now, the goal here is when we add the silver in this particular problem, we want only this guy to basically make it solid. We want the chloride to still be floating around basically in the solution and not be affected at all. Now, why would you want to do this and just maybe take out one guy first and leave the other guy floating around? The reason is you want to make sure in some cases that you got rid of, for example, the bromide and you still have chloride in your test tube. Why would you have to worry about being careful when you do that? The reason is, frankly, when you add silver to this situation, you're basically going to get two white precipitates that are going to form. So you can't look in your test tube and go, I think this one is the silver chloride, and I think this one is like the silver bromide. You would have no way really to know which one's which because they're going to be basically the same color. There won't be different colors to tell you, oh, the red one's this one or the yellow one's this one. But because they're both obviously going to be kind of a white precipitate, you really will not have a way to really understand which one you actually precipitated out or which one's which. So the selective precipitation is really this idea of using KSP and basically figuring out how we could just basically ultimately reach in there and just kind of take one ion out of the solution at a time. And we can use the KSP to help us do that. And if we look at really our two sort of KSP reactions here, we have silver bromide, which has a KSP value of 7.7 times 10 to the minus 13. And we have silver chloride, which has a KSP value of 1.6 times 10 to the minus 10. So what we do know, though, is the concentration of each of these ions in here. They both have a concentration of 0.02 molar, basically. So each of them are 0.02 molar. So we could actually use our KSP expression here, say for our first one. Our KSP would be the silver concentration times the bromide concentration, and that would equal 7.7 times 10 to the minus 13. Now I am looking for the silver concentration. So if I take the silver concentration and divide the KSP by the bromide concentration, and again, I do have that number, which is the 0.02 molar. That would tell me that the silver concentration here would be about 3.9 times 10 to the minus 11 molar. So what does that number really mean? So this is the concentration of silver. This is basically the minimum concentration of silver to see silver bromide precipitate out. So you minimally got to get your silver concentration to 3.9 times 10 to the minus 11. And when you do that, if you took this guy at 3.9 times 10 to the minus 11, you dumped it in there, that is enough to go find the bromide ions, and you will start to see a white precipitate basically form at this point. Now, we could do a similar calculation here for silver chloride, where the KSP is going to be our silver ion times our chloride ion, which will equal 1.6 times 10 to the minus 10. Once again, solving for the silver concentration, which is what we're interested in this case. Dividing it by the concentration of the chloride will give us a concentration of 1.6 to the minus 10 by 0.02. Call it 8 times 10 to the minus 9 molar. This number is the minimum silver concentration to precipitate out silver chloride in this case. So what does this mean? It means that if you keep your silver concentration greater than 3.9 times 10 to the minus 11 molar, you will start to see a precipitate form. And that precipitate is going to be silver bromide, and that's where it starts to precipitate out. That's because you need actually a lot more silver concentration. You need about 8 times 10 to the minus 9 to start to see silver chloride basically precipitate out. So if you add silver at a concentration of 3.9 times 10 to the minus 11, you will see this white precipitate out. You could continue to increase the concentration of silver as long as you keep it under 8 times 10 to the minus 9, and you will continue to see white solids come out. And you can feel pretty confident at that point that the white solid that you're seeing is the silver bromide that's precipitating out. If you were doing this in real life, at some point you would stop seeing basically a precipitate, hopefully. And at that point, if you rose the silver concentration to 8 times 10 to the minus 9, which is a larger concentration, you would once again start to see a white precipitate. And at this point, that white precipitate would be the actual silver chloride starting to precipitate out. And by controlling the silver concentration, you could selectively go in there and just grab out the bromide ions as silver bromide. And once you've done with that, you could then go in there and grab out the chloride ions as silver chloride. Question on that there. Could we have predicted based off the KSP values here, which one should precipitate out first? The answer is yes, we could, because silver bromide breaks apart into 2 ions. Silver chloride breaks apart into 2 ions, which means when we look at the KSP values between these two, we see that silver bromide is a smaller KSP value, which means it's going to be more insoluble than silver chloride. And that's why the question asks that question, which is how can you do the silver bromide first, right? What would happen in this case, though, that I didn't follow anything, didn't do any calculations, thinking I did not need to do, and I just dumped in there a silver concentration right off the bat of greater than 8 times 10 to the minus 9, what would happen? everybody's just going to precipitate out together, right? You're going to get the bromide to precipitate out because that's plenty to get that guy to come out. You'll get the chloride to come out all at once, right? So if you started at a concentration higher than this concentration here, you would get it just everybody to precipitate out at once, and you would not be able to know which one's which. Any questions on that? So selective precipitation is a procedure that's very common with KSP. Again, like I said, we don't actually do those experiments anymore, but there's a bunch of experiments which are known as qualitative analysis type of experiments. And it's really all about using KSP to your advantage to precipitate out ions that you want to precipitate out of solution and leave other ones floating around until you're ready basically to precipitate those guys out. Any questions on that there? So this is sort of that qualitative analysis. And when we talk about sort of that type of experiment, the idea there is there's different groups. There's group 1, group 2, group 3, group 4, and group 5. Sometimes these guys are comboed together. These, by the way, are groups that are not based on the periodic table, but they are grouped together based on solubility. So if you look at group 1, which is silver, mercury, and lead, that basically is your chloride exceptions, silver, mercury, and lead, and they're all part of what's known as group 1. Group 2 has some other guys in there, some cadmium, copper, bismuth, and all those kind of guys as well, group 3 and so forth. When you get down to group 4 or 5, you get a lot of things that are soluble in everything, like potassium, sodium, and ammonium. And what happens when you do these experiments is at that point, there's not a lot of things that you could add to get them to precipitate out to sort of verify what you do, something like a flame test, and you'll be able to sort of predict what ions were in the solution. Now, each of these groups actually have a specific reagent that will precipitate it out. So typically speaking, if you had group 1, you would hit it with HCl. The Cl is actually chloride part of it is what's going to precipitate out those group 1 ions. What that typically would do if you had like an unknown where you had in a beaker floating around group 1, 2, 3, 4, and 5 ions floating around there, the idea is you would want to add something like chloride. That would only take group 1 out as a solid. All the rest of the guys would still be floating around. Then you could go take out group 2. Group 2 actually uses hydrogen sulfide gas, which is really smelly, so you should be really happy you don't do it. Sulfide everywhere. But it uses sulfide basically as the precipitating ion. And actually, group 3 actually uses sulfide as well, hydrogen sulfide. But there is actually a difference between group 2 and group 3. Even though they use the same sulfide, it is what we were just talking about. The pH is different between these two. In group 2, the pH is super acidic, like 0.5 pH. You make it super acidic. And in group 3, you actually switch it to basic. So you could actually use, again, the same precipitating reagent, but because you affected the pH like we were talking about, affecting the pH in the acidic way will keep all those group 3 ions still floating around, and affecting the pH in the basic way will then allow them to precipitate out. Like I said, at the end, a lot of times you'll do some flame tests to identify these ions that are around, and that sometimes is a good way to do those things. All right, any questions on KSP? The next thing we're going to talk about is complex ion equilibrium. And when we have a complex ion, it is basically a metal, and a lot of times it's those kind of transition metals that are in the middle, and there's some type of ligands that are attached. And ligands are Lewis bases. And if you remember, a Lewis base is something that will donate a pair of electrons. So remember that a Lewis base is something that will donate a pair of electrons. And that is usually things, for example, that are negatively charged because they have extra electrons. That's also things like water is a very common Lewis base, things like ammonia, which are polar and have non-bonding electrons on that kind of electronegative element, will allow them to do that. It will actually set up an equilibrium here. So the cobalt plus the chloride will make our complex ion here, which in a later chapter, you'll know how to properly name that. And Since it is an equilibrium, we can set this up as an equilibrium constant, and this gives us our formation constant, which is basically the equilibrium constants for complex ions. It's the same deal. We're going to take products divided by reactants. We also need to obviously take our coefficient and use it there as our exponent. When the Kf value is large, that means we have a lot of complex ions, and the equilibrium will go to the right-hand side, and the complex ion will be formed. Now, these ligands actually come on one at a time. So although we're adding 4 ligands here, and again, in this case, it is the chloride here. That's our ligand, right? Our Lewis base. They actually do come on one at a time. It's a stepwise sort of fashion. So the cobalt will react with one chloride, and that will give you something like CoCl plus. And you could have a equilibrium constant for that little step. The next thing that would happen is this guy that has a +1 charge will pick up another chloride and make CoCl2. Again, also could have an equilibrium expression or constant for that step. This guy here will then pick up another chloride. And make CoCl3 minus. Could also have an equilibrium for that. And lastly here, this guy here will pick up our last chloride. And we'll make CoCl4 2 minus. And you could also have one for that. That, by the way, is how we get to our overall reaction, because these are all equilibrium reactions, which means when we add these together, this guy cancels, this guy cancels, this guy cancels, leaves us the overall reaction we see up on top, which is the cobalt plus 1, 2, 3, 4 of those. Makes our complex ion, right? Which would be our Kf value. By the way, if I knew just these numbers and I wanted to calculate the Kf for this, what should I do with those numbers? Add, subtract, multiply, divide? You should, yes, good answer. You should multiply, right? So you should multiply those guys together, right? Remember, when you add up equilibrium expressions, the K values get multiplied to figure out the equilibrium constant at the end. Any question on that there? So sometimes in these problems, you will be given kind of the overall reaction with the Kf value. Sometimes you may be given just the individual steps along the way, and you can add it together, get the overall reaction and the K value. Now, Kf, unlike KSP, which is typically very small values, Kf values are actually typically really large values. So they're like the other end of the extreme. So Kf values are extremely large values, like to the 50, to the 40, 36, really large sort of values. And what that means is, typically speaking, when we see Kf values and this complex ion, pretty much the equilibrium definitely wants to go to the right, because they're really, really large values of K. So we're going to get a lot of products being formed. And what that means is that we typically will see the complex ion definitely wanting to form. Now, as I mentioned before, ligands, which are Lewis bases, are usually things that are polar, have again, those non-bonding electrons, are things that are negative. There's also, when we talk about complex ions, something known as coordination number. And coordination number, we'll get a little bit more into it, is actually the number of atoms directly attached to the metal. So for example here, that cobalt basically is attached to, and I won't draw them all out, but basically here's 6 waters. And each water will attach to the hydrogen, which means basically in this case, there's 1, 2, 3, 4, 5, 6 oxygen atoms that are directly attached to the metal. And that's why it has a coordination number of 6. Same thing with the cobalt one. It basically has 4 chlorides attached, and that will give it its coordination number 4. Now, ligands, as we will see in a later chapter, there are certain ligands which are referred to as being monodentate, and that basically means that that molecule or ligand will attach only through one atom to the metal, like we see with water or we see with chloride. But there are some ligands, for example, like oxalate. Looks something like this. C2O42 minus. Oxalate actually was known as a bidentate ligand because at both of those oxygens that are single bonded, it can attach to the metal. So you get like a 2-for-1 action when you have a oxalate molecule. Basically, if you had 2 oxalate molecules, that would mean that if you had 2 of them attached to this metal, 1, 2, 3, and 4, this would have a coordination number of 4, even though you basically have a metal and 2 oxalates there, right? The number down there is the bottom. Sometimes people think the little subscript next to the ligand is always what the coordination number is, but it actually does depend on the type of ligand that's there. In this case, with oxalate, even though there's only 2 of them, each one binds twice per molecule, which basically gives you a coordination number of 4. Any questions on that there? And we'll see more of that in a later chapter when we talk more about complex ions. All right, so let's talk about how we go about doing these type of problems. And it's a little bit different than some of the calculations that we've done before. We do make some sort of assumption based on the KF value. So let's talk about what's going on here. So we take zero point 0.2 moles of copper 2 sulfate and we mix it with 1.2 molar of ammonia. What is the concentration of copper 2 at equilibrium, the copper 2 ion at equilibrium? So we have this equilibrium here. This is the overall equilibrium equation. Again, each of those ammonias would be added one at a time, gives us our KF value in this case. In this case, we're just going to assume that all the volumes in this case are going to be 1 liter total, and that's not going to change. Once again, in other problems, you won't assume that. You'll just have to take the volume into account. So we're going to do an ice table here, and really what we want to do is this ice table, we most likely want to do it in molarity. So we want to get the molarity of everybody. So the copper 2 is all going to come from the copper 2 sulfate. And if I have 0.2 moles of it, and I'm going to assume that everybody's volume is 1 liter, that will basically give me 0.2 molar as my starting amount here for my copper 2 ion. Same thing here with my ammonia. I'm going to assume again that it is basically 1 liter, which will give me 1.2 molar as well. And we will have 0 here. Now, normally when we do these sort of ice tables with molarity, we typically use X's, right, to kind of do the change part. So normally what we would do is we would roll through this ice table and go, okay, the change is going to be minus X, uh, not plus. Let's try that again. Minus 4x here. And plus x on this side, again, taking in their coefficients. Now, the first assumption that we make when we do these problems is based off of the KF value. So as I mentioned before, these are usually very large values. And we assume that essentially all of the metal ion gets used up. And that's because of the large value of K, we would expect essentially, even though it is a reversible reaction, it is almost going to be like a one-way reaction heading towards the product side because of the really, really large K value. So because of that really large K value, we assume that even though it is a reversible reaction, it's all going to pretty much drop out there on the product side. It's all going to go one way. And because of that, the metal in these type of problems are typically the limiting reagent because it's the guy in the center and then all these ligands just attached to it, and they pretty much the metal gets used up in this case. So the assumption we make is that that metal gets used up. So instead of using X's in this table, we actually will, I'll put an extra C in there. How's that? We'll just kind of box that guy. What we typically will do is just actually use the number. So 0.2 minus 0.2. This would be then minus 4 times 0.2, and this would be plus 0.2. Then we could basically carry down and get some numbers. This obviously is going to be 0.2 minus 0.2, and that will give us 0. This will basically be 1.2 minus 4 times 0.2, which will get us here 0.4 molar. And here we will get 0.2 molar. First off, any question on that first assumption? So pretty much if you do these problems, it's going to be your metal. Your metal is going to be the change part of it. So basically you could substitute the concentration of the metal in for X when you normally do your minus X's, your plus X's. Any questions on that? Now, clearly at this point, or even before, we could have wrote our equilibrium expression, which would be our complex ion divided by the copper concentration times the NH3. And again, we do need to take it to the fourth. And obviously here, that's our 5 times 10 to the 13th. Now, you may be saying, I'm looking for the copper 2 concentration at equilibrium. And frankly, I just zeroed it out. So can I just write 0 and be done with it? The answer is no, because that would have been a very quick problem if you could have done that in all these problems. The idea here is the second part of the assumption is, although we assume that pretty much all of that copper 2 in this case is going to get completely used up to make this complex ion, it is unfortunately still a reversible reaction, which means even though almost 100% of it's going to go to the product side, there is still going to be just a little bit of it that's going to want to come back to the reactant side. So we're going to get a little bit of it coming back the other way. So what we do in this situation is, even though we zeroed out the copper 2 concentration, because it's a reversible reaction, frankly, we do know that some of it should come back the other way. The other assumption that we make is the amount that comes back the other way should be like really, really small. So we should end up with a really, really small concentration of free copper in this case, ions, because pretty much 100% of it should be used up in the actual complex ion on the product side. So we call it X, and now we could go into our equilibrium expression here with our equilibrium values. And if we do that, that will give us basically 0.02 up on top, divided by the copper concentration, which is what we're looking for, times our 0.4, which again, we do need to take to the fourth, and that will equal our KF value of 10 times, 5 times 10 to the 13. We want to rearrange this, and if you're not sure, basically these two guys just switch places. We multiply the copper 2 to the other side and then divide by, so you're basically going to multiply the copper 2 to both sides and then come back and divide by 5 times 10 to the 13. That essentially will give you 0.02 divided by 5 times 10 to the 13. It is 0.2. Thank you very much. Thank you. It is 0.2 there. Added me an extra 0 for free. There we go. Thank you. It is 0.2, so pop that into 0.2. There we go. All right, so we got our 0.2, our 5 times 10 to the 13, and our 0.4 that we again still need to take to the fourth, and that will equal our copper 2 concentration in this case. All right, so we'll go 0.2 divided by 5 to the 13 divided by 0.4 to the 4th. And I'll get us something like 1.6 times 10 to the minus 13 molar is the amount of free copper 2 in that actual solution. That's a large number or small number? It's a super small number, right? And that validates our assumption that pretty much all of the copper 2 ended up on the product side in that complex ion. Barely nothing is still floating around free in that solution, pretty much close to zero. But again, there's still going to be just a little bit of it still in the solution freely floating that did not get kind of used up in that complex ion. Questions on that there? Yeah. The 0.4 comes from doing the 1.2 minus 4 times 0.2, I hope. Just double check I didn't add an extra zero on that, but that's where it should come from there. Yeah. So it's basically the same idea in a normalized table. We would take 1.2 minus 4x. In this case, though, we already know what x is going to be based on our assumption that's going to be the metal ion that's free. So we can kind of just put the number in without having to do the x and stuff like that. Other questions? All right. So I think what we're going to do is we're going to lay it up there for now.